Hello, fellow space explorers. Before we dive into today's journey through the cosmos, don't forget to click the like button if you like this kind of content and subscribe to our channel for more exciting space discoveries. So let's embark on a mind-bending adventure and unravel the mysteries of the universe. Today, we're taking you back to the beginning of time itself, to the event that created everything we know, the Big Bang. Around 13.8 billion years ago, the universe was born from an incredibly hot and dense point, which then rapidly expanded in a monumental event we call the Big Bang. This explosion wasn't just any explosion. It was the birth of time, space, matter, and energy, the genesis of the cosmos. The Big Bang is the beginning of the universe and the foundation of our cosmic story. In the moments after the Big Bang, the universe began to expand and cool at an astonishing rate. During these first fractions of a second, the universe was unimaginably hot, so much so that matter and energy were inseparable. The basic building blocks of all matter, particles such as quarks, leptons, and photons, moved freely in a chaotic primordial soup. These were the fundamental building blocks of our universe, dancing in a cosmic ballet amidst the chaos. As the universe continued to cool and expand, order began to emerge from this initial pandemonium. Within the first few seconds, quarks began to bind together to form protons and neutrons, the fundamental particles of atomic nuclei. These particles would go on to form the first light elements, mainly hydrogen, helium, and traces of lithium. These elements laid the groundwork for the chemical composition of the universe and are, in fact, the building blocks of the stars and galaxies that would come billions of years later. About 380,000 years after the Big Bang, something extraordinary happened. The universe had cooled enough for protons and electrons to combine to form neutral hydrogen atoms. This process made the universe transparent for the first time, allowing light to travel freely. This event also gave rise to the cosmic microwave background, radiation, CMB, a faint but pervasive glow that we can still observe today. The CMB is like a snapshot of the infant universe, a whisper from the early days of the cosmos that provides crucial information about the state of the universe in its infancy. This ancient light, this cosmic relic, holds the secrets of the early universe and provides scientists with an invaluable tool for understanding how it all began. The patterns and fluctuations in the cosmic microwave background give clues to the distribution of matter and energy in the early universe, and provide insights into the formation of galaxies, stars, and planets. But the early universe wasn't just home to matter, it was also home to antimatter. Antimatter is made up of particles that have opposite charges to normal matter. For example, while protons carry a positive charge, their antimatter counterparts, antiprotons, carry a negative charge. In the early universe, there may have been equal amounts of matter and antimatter. Today, however, the universe seems to be dominated by ordinary matter, with antimatter being incredibly rare. What happened to all the antimatter? This question has puzzled scientists for decades. One theory is that a small asymmetry in the behavior of matter and antimatter in the moments after the Big Bang caused more matter to survive than antimatter. This tiny imbalance may be responsible for the existence of the universe as we know it today. Without this asymmetry, matter and antimatter could have annihilated each other, leaving behind a universe devoid of stars, planets, and life. Understanding antimatter is crucial to unlocking the deeper mysteries of the universe. Modern experiments, such as those at particle accelerators, like the Large Hadron Collider, allow scientists to create and study antimatter in a controlled environment. These experiments are shedding new light on the nature of antimatter and helping to unravel the complex puzzle of why the universe is predominantly made of matter. The mystery of antimatter remains one of the most intriguing questions in modern physics, and solving it could be the key to understanding the earliest moments of the universe. But the Big Bang didn't just create matter and antimatter, it was also the beginning of time and space itself. The immense energy unleashed by the Big Bang set the universe in motion, triggering the formation of galaxies, stars, and planets. The cosmic expansion that began in those first moments continues to this day, as confirmed by the observations of astronomer Edwin Hubble. He discovered that the universe is still expanding, and that this expansion is a direct result of the energy released in the Big Bang. The Big Bang theory is the cornerstone of modern cosmology, Observational evidence such as the cosmic microwave background radiation, the abundance of light elements, and the continuing expansion of the universe all support this theory. Understanding how the universe has expanded and evolved over billions of years allows us to trace the origins of cosmic structures such as galaxies, stars, and planetary systems. But the Big Bang is only the beginning of the story. The forces and processes that shaped the early universe, from the formation of the first atoms to the complex web of galaxies we see today, continue to shape the cosmos. As we look deeper into the universe, we uncover more of its incredible history, revealing the wonders of how matter, energy, and gravity work together to create the vast and intricate cosmos we now explore. Dark matter is one of the most puzzling phenomena in the cosmos. Although it doesn't emit, absorb, or reflect light, dark matter makes up about 27% of the universe's total mass and energy. Unlike ordinary matter, which we can observe in the form of stars, planets, and galaxies, dark matter is invisible and interacts with ordinary matter mainly through gravity. So how do we know that it exists? One of the key pieces of evidence for dark matter comes from observing the rotation of galaxies. According to the laws of gravity, galaxies should rotate in such a way that the outer stars, far from the galactic center, move more slowly than those closer to the core. However, observations show that stars at the outer edges of galaxies move just as fast as those near the center. This suggests that some unseen mass is exerting an extra gravitational pull, holding these stars back from flying out into space. This unseen mass is what we call dark matter. Another important clue comes from gravitational lensing. This occurs when light from distant galaxies is bent as it passes through massive objects, such as clusters of galaxies, on its way to Earth. The amount of bending is greater than can be explained by the visible matter in these clusters. This suggests the presence of dark matter, which adds to the gravitational pull. Dark matter plays a crucial role in the formation and evolution of cosmic structure. In the early universe, dark matter clumped together under the influence of gravity, forming massive structures known as dark matter halos. These halos provided the scaffolding around which galaxies formed. Without dark matter, galaxies as we know them wouldn't exist. They would have scattered long ago because the gravitational forces would have been too weak to hold them together. Scientists have proposed several candidates for dark matter particles, but none have been directly observed. Some of the leading hypotheses include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. These particles are thought to interact only weakly with ordinary matter, making them incredibly difficult to detect. Nevertheless, researchers are conducting experiments in underground laboratories and particle accelerators around the world to try to catch a glimpse of these elusive particles. Understanding dark matter is crucial not only for explaining the structure of the universe, but also for unraveling fundamental laws of physics. As mysterious as dark matter is, dark energy is perhaps even more puzzling. While dark matter acts as a kind of cosmic glue, holding galaxies and structures together, dark energy does the opposite. It pushes the universe apart, driving its expansion at an accelerating rate. Dark energy was discovered in the late 1990s when astronomers studying distant supernovae noticed something strange. The expansion of the universe wasn't slowing down, as expected, but speeding up. This was a groundbreaking revelation, as it suggested the presence of a force counteracting gravity on cosmic scales. Dark energy makes up a staggering 68% of the total energy content of the universe, dwarfing both dark matter and ordinary matter. Despite its dominance, we know very little about what dark energy actually is. Some theories suggest it may be a property of space itself, a kind of vacuum energy that exerts a repulsive force. Others suggest that it may be related to some new, undiscovered area of physics that we have yet to understand. What we do know is that dark energy is driving the expansion of the universe, and its influence is increasing with time. This accelerating expansion has profound implications for the future of the cosmos. If the trend continues, the universe could end in what scientists call the Big Freeze, or heat death, where galaxies become so far apart that stars burn out, leaving a cold, dark, and empty universe. However, there are still many uncertainties surrounding dark energy, and future observations may reveal new insights that could dramatically change our understanding of the fate of the universe. To explore these questions, scientists are using powerful telescopes such as the Hubble Space Telescope, and upcoming missions such as the James Webb Space Telescope to map the expansion of the universe in more detail. These observations will help us understand how dark energy has affected the universe's growth and provide clues to its true nature. Now let's travel back to a time just after the Big Bang, when the universe was young, dark, and largely featureless. After the formation of hydrogen atoms, the universe entered what we call the cosmic dark ages. For several 100 million years, there were no stars, no galaxies, just a vast dark expanse filled with hydrogen gas. But all that changed with the formation of the first stars. These early stars, known as population 3 stars, were much bigger and hotter than the stars we see today. They formed when clouds of hydrogen gas collapsed under gravity, igniting nuclear fusion in their cores. These first stars marked the end of the Dark Ages and flooded the universe with light for the first time. As these stars burned through their fuel, they created heavier elements such as carbon, oxygen, and iron in their cores. When these massive stars reached the end of their lives, they exploded in powerful supernovae, ejecting these elements into space. This process seeded the cosmos with the building blocks for future stars, planets, and eventually life itself. The first stars also played a crucial role in the reionization of the universe. By emitting intense ultraviolet radiation, they ionized the surrounding hydrogen gas, stripping electrons from atoms and turning the gas into plasma. This process, known as cosmic reionization, allowed light to travel more freely through the universe and paved the way for the formation of galaxies. Over time, small clumps of matter began to coalesce under the force of gravity, forming the first galaxies. These early galaxies were much smaller and less organized than the massive spiral and elliptical galaxies we see today. But through billions of years of merging and interacting, these proto-galaxies evolved into the complex structures that populate the universe. As galaxies formed and grew, so too did another mysterious cosmic entity, black holes. These objects are among the most puzzling and powerful phenomena in the universe. A black hole is a region of space where gravity is so strong that not even light can escape its grip. Black holes are formed when massive stars collapse at the end of their lives. These stellar remnants can be only a few kilometers across, but they contain the mass of several suns, creating a gravitational pull that distorts space and time. At the center of many galaxies, including our own Milky Way, are supermassive black holes. These cosmic giants are millions to billions of times more massive than the Sun. How they form remains one of the greatest mysteries in astrophysics. Some theories suggest that they were formed by the collapse of massive gas clouds in the early universe, while others suggest that they grew by accreting matter over billions of years. Despite their name, black holes are not entirely black. As they suck in matter from their surroundings, they form accretion disks, spirals of gas and dust that heat up as they fall towards the black hole. This process releases enormous amounts of energy, creating jets of particles that can stretch for vast distances. In fact, some of the brightest objects in the universe, known as quasars, are powered by supermassive black holes at the centers of galaxies. By studying black holes, scientists not only learn about the life cycles of stars and galaxies, but also gain insights into the fundamental nature of space and time. Black holes challenge our understanding of physics, particularly when it comes to reconciling the theories of general relativity and quantum mechanics. As we continue our journey through the cosmos, we venture into some of the most puzzling and fundamental aspects of the universe. The realm of quantum mechanics, mysterious quantum entanglement, and the possibilities of the multiverse. These ideas bridge the smallest scales of reality, from subatomic particles to the vast structure of the universe, showing us that the cosmos operates on a level that can seem as strange and incomprehensible as it is magnificent. At the heart of the universe is the quantum realm. Unlike the classical world we observe with our senses, where objects behave in predictable ways, the quantum world operates according to rules that defy our everyday experience. In the quantum realm, particles such as electrons and photons don't follow the familiar rules of Newtonian physics. Instead, they exist in a state of probability where their location, speed, and other properties are uncertain until they are measured. This is encapsulated in Heisenberg's famous uncertainty principle. One of the core principles of quantum mechanics is the idea that particles can exist in multiple states simultaneously, a phenomenon known as superposition. A well-known illustration of this concept is Schrödinger's cat, a thought experiment in which a cat in a box is considered to be both alive and dead until the box is opened and its state observed. At the quantum level, particles behave in this strange way, existing in all possible states until they are observed, at which point they collapse into one particular state. But the weirdness doesn't stop there. Particles in the quantum world can also become entangled. This means that the state of one particle is directly linked to the state of another, even if they are separated by vast distances. This phenomenon, known as quantum entanglement, was famously described by Albert Einstein as spooky action at a distance. But despite its apparent strangeness, entanglement has been experimentally verified many times. Quantum entanglement is challenging our understanding of space and time. When two particles become entangled, their properties are linked so that a change in one particle instantly affects the other, no matter how far apart they are. If one particle is measured and found to be in a particular state, the other particle will be in the complementary state, even if it is on the other side of the universe. This raises profound questions about the nature of reality. How can information be instantaneously transferred between entangled particles if the speed of light is the universal speed limit? This paradox has led some physicists to speculate that there may be hidden dimensions or deeper connections between the fabric of space and time that we don't yet understand. Others suggest that entanglement reveals something fundamental about the non-locality of the universe, the idea that space itself may not be as absolute as we think. In recent years, quantum entanglement has found practical applications, most notably in the field of quantum computing. Quantum computers harness the power of entangled particles, called qubits, to perform calculations at speeds far beyond those of classical computers. This could revolutionize fields such as cryptography, artificial intelligence, and even our understanding of the universe itself. As we delve deeper into the quantum realm and the nature of space and time, we encounter a provocative question. Is our universe the only one? The idea of a multiverse, that there could be an infinite number of parallel universes, each with its own set of physical laws and constants, has gained traction in both theoretical physics and cosmology. The multiverse theory arises from several different areas of research. One of the main drivers is the concept of cosmic inflation, the idea that the universe underwent a rapid expansion shortly after the Big Bang. Some versions of inflation theory suggest that this expansion never stopped completely, and that pocket universes continue to form in distant parts of the cosmos. Each of these universes could have different laws of physics, leading to radically different forms of matter, energy, and even life. Another source of multiverse speculation comes from string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. String theory predicts the existence of many possible vacua or energy states, each corresponding to a different type of universe with its own unique properties. These could include universes where gravity is much stronger or weaker than in ours, or where time and space behave in completely unfamiliar ways. If the multiverse exists, it raises profound philosophical questions. Are there other versions of us in these parallel universes? Could choices we make in this universe lead to different outcomes in others? These ideas may sound like the stuff of science fiction, but they are based on serious scientific research. However, as other universes may be completely isolated from ours, it's unclear whether we could ever observe or interact with them. Despite the speculative nature of the multiverse theory, it offers a potential solution to some of the deepest mysteries in cosmology. For example, why does our universe seem so perfectly tuned for life? The values of fundamental constants, such as the strength of gravity and the charge of the electron, are just right for stars, planets, and life to exist. In a multiverse, this apparent fine-tuning could be explained by the existence of countless other universes where the constants are different and life doesn't arise. We just happen to live in one of the rare universes where everything is just right. Returning to the observable universe, we see that galaxies aren't randomly scattered across space. Instead, they form an intricate cosmic web, a vast interconnected structure of galaxies, clusters, and superclusters that stretches across the universe. This web-like structure is the result of gravity acting on the universe's dark matter and ordinary matter over billions of years. The cosmic web is made up of filaments, where galaxies are concentrated, and voids, which are vast, empty regions of space. These filaments of galaxies are connected to each other, forming a web-like pattern that extends over hundreds of millions of light years. This structure reveals the grand scale of the architecture of the universe, with galaxies acting like beads on a string within the filaments. At the intersections of these filaments are galaxy clusters, massive gravitational centers containing hundreds to thousands of galaxies. These clusters are held together by both dark matter and the gravitational pull of their individual galaxies. Studying the cosmic web helps scientists understand how the large-scale structure of the universe evolved from the initial density fluctuations in the early universe. The cosmic web is also a key component in understanding how galaxies grow and evolve. Galaxies that form along filaments often collide and merge with each other, triggering bursts of star formation and reshaping their structures. This process of galactic interactions and mergers is one of the driving forces behind the evolution of galaxies over cosmic time. As we continue to explore the vastness of space, we face one of the biggest questions of all. What is the ultimate fate of the universe? There are several possible scenarios for how the universe will evolve in the distant future, and much depends on the nature of dark energy. If dark energy continues to drive the expansion of the universe at an accelerating rate, we could be heading for a big freeze or heat death. In this scenario, galaxies will drift further apart, stars will burn out, and the universe will become a cold, dark, and empty place. Alternatively, as the influence of dark energy weakens over time, gravity could eventually take over, stopping the expansion and causing the universe to collapse in a big crunch. In this scenario, the universe would shrink back to a single point, possibly leading to another Big Bang and the birth of a new universe. There's also the possibility of a big rip, where dark energy becomes so powerful that it rips apart galaxies, stars, planets, and even atoms, ending the universe in a violent rupture. While the ultimate fate of the universe remains uncertain, one thing is clear: the cosmos is constantly changing. From the formation of the first stars and galaxies to future scenarios of cosmic death, the universe is an ever-evolving tapestry of matter, energy, and forces, all woven together by the fundamental laws of physics. As we've traveled through the vastness of space and time, from the Big Bang to the mysteries of dark matter, dark energy, and quantum mechanics, it's clear that our understanding of the universe is still evolving. Each discovery raises new questions, and the more we learn, the more we realize how much remains to be explored. The cosmos is a place of infinite wonder, full of phenomena that challenge our understanding of reality. From the strange behavior of particles in the quantum realm to the majestic structure of the cosmic web, the universe is a place where the very small and the very large are deeply interconnected. As we look to the future, the quest to understand the cosmos will continue to push the boundaries of human knowledge. Whether through telescopes peering into the distant universe, experiments exploring the quantum realm, or bold new theories about the multiverse, our journey of exploration has only just begun. And who knows, we may one day unlock the deepest secrets of the universe, or even discover other realities beyond our own. Until then, the stars above us will continue to inspire wonder, curiosity, and the never-ending quest for knowledge.